My name is Anthony Pepitone, and this is Lab 3, Magnetic Field of a Bar Magnet. So the purpose of this lab is to find, measure, and understand the distances and how they correlate to the magnetic field and the magnetic dipole moment of a bar magnet. The fundamental principles is going to be a lot of calculations of the magnetic fields, including on-axis, off-axis, and perpendicular, along with the Biot-Savart law, and a brief preview of the results shows that the difference between the experiment and the computational model is they're pretty similar, but they're off by just a little bit, which could have been a couple errors on my end. So there's a lot of equations in this lab. There's almost too many equations for this lab, including the Biot-Savart law, the magnetic field of a ring, the dipole of a ring, a magnetic dipole moment, on-axis B field, a perpendicular axis B field, and the B field off of axis. So listed here is all those equations, if you need to see them. So for the system and surroundings, the system is going to be our magnet, and then the surroundings is going to be everything else, including the phone, any like measuring tape, and the meter stick, all that stuff. It's all going to be the surroundings. So for the experimental data, after we set up the phone and found the correct distances, we were able to get this data as shown, which gives us in the top section the on-axis B fields, whereas the bottom section shows us the off-axis B fields. And as you can see with the inverse log, we get this little graph as shown for the magnetic field and the distances. So some questions for the observation summary after the experiment was conducted. We have when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. We saw that that was true as the further you get it away. Next question, as the magnetometer moves closer to the magnet, the measured x component of the magnet field decreases. We saw that it actually didn't. The position of the magnetometer has no effect on the measured x component of the magnetic field. Along with this, we saw that it didn't. And lastly, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. We saw that it actually did. So now we can get into the code for the computational model. There's a lot of lines of code. I don't know why we have that many lines, but so starting off, we have our physical constants, which is going to be the mu naught over 4 pi, which is 1 e to the negative 7th. Along with this, we have to create our magnet at the origin. So that's just a bunch of stuff to create that magnet and that point. The function under that is going to be to create the magnetic field, which we're taking the constant times 1 over r cubed times each direction in the x, y, and z, and multiplying that by r hat times mu. Along the left side, we also have the scales and the distances, which allow for our arrows and things to be seen more accurately in the code model. On the right side, we have a lot of arrows being made for all of the perpendicular fields and all that. So we have 4 arrows there, we have 4 arrows at the bottom. Those are all just creating the magnetic field arrows. For the next part of the code, because we need 2 parts because there's a lot of code, we're taking the 45-degree off-axis magnetic field. So we need to calculate that. We're calling that dperp. We're going to print that at the end as well. Along with this, we have the observation locations and the arrows for the off-axis magnetic field. So after I personally did all of the modeling and experimenting myself, I saw that the perpendicular stuff was pretty close, and while it's cut off on the bottom here, the perpendicular field was pretty close as we saw in the brief preview of the results. So some things could have been my taking into account Earth's magnetic field, along with some other things maybe just in the phone and getting the exact distances, which could have thrown off our results a little bit. For our first what if question, we are being asked, what if we hadn't oriented the experiment to compensate for the Earth's magnetic north, and how would our results have changed? We can say that the results all would have been different by the same amount because we're not taking into effect the Earth's magnetic field, so it would throw all our results off by the same amount. So it would make our computational model a little bit more different than the experiment, but all by the same degree. And for our second what if question, what if we were to take 2 identical magnets together? How would we expect the measurements to differ? The measurements would differ by some constant that would be created by having a greater magnetic dipole moment. So everything would be sort of in the same thing, but just kind of multiplying it by all the same constant. Thanks for watching. I loved this lab the most that I've ever done any other lab.